So now's the time for the bees in your bonnet to buzz, if you have any bees in your bonnet. I'll ask for questions first from non-specialists and non-scientists, if there are any, and then anybody at all. And if you're close to a mic in the centre, could you use it, please? And if not, just shout. So Alan Lobach, who knows nothing about climate.
Now, I have a question about a philosophical question about your first slide. It's not a thing I'm a special.
David Bamble, or?
No, for you.
Oh, okay.
You said that your hypothesis was that there are two camps when it comes to climate communication. One is scientists, and then one is the press. But I think you might have left out one of the camps, which is the massive disinformation campaign that's funded by global warming deniers. And then your hypothesis was these books are going to solve this problem which you posed and fill in the gaps. And I was wondering if there's any scientific research that supports this claim, the fundamental hypothesis of the series. Do you think that these books are really going to solve the problem, and is that really the problem? And I'm not an expert in that, that's why I raised my hand.
I mean, I'm not an expert in it, so perhaps Alison will answer. But I mean, I think I was perhaps oversimplifying. I mean, there's certainly a spectrum of communication from the very technical to the very simple, and we're somewhere in the middle. I would be very pleased if we solve the problem. I would be doubtful if we will solve the problem, but perhaps. Alison, do you want to?
In general, we noticed that there was a gap between, you have your high-level literature, the textbooks, and the IPCC report, and more popular accounts, and all of those play an important role. And we just noticed that we were particularly at a moment where there was an increasing need for, scholars coming from other fields, students, to occupy this middle ground of a sophisticated treatment of climate that didn't also require tremendous background, and also could be found in what could seem to be short, readable books, so you don't have to look at the internet for all the journal articles. And we have wonderful authors who are authorities to speak authoritatively on this, so you know what you're reading is backed up by great science and research. So I don't know if that answers the question, but that's the goal for.
No, that all makes sense. I was just wondering about active disinformation.
Mm-hmm.
And does it help solve that problem when people try to mislead you? And spend a lot of money doing that, and have been rather successful in the United States.
I don't know that I'm the best to speak to that. I mean, maybe Andrew Revkin, this afternoon, our keynote speaker, who spends a lot of time with climate communication, can speak to that more directly.
Yeah, hi. Is this on? Yeah, it sounds like it's kind of on. I mean, you could probably hear me. So I just have a basic question. You guys gave us a very nice outline of the basic kind of movement of climate science. I would like to ask about the frictions, particularly between the ecological side and the maybe more climactic and atmospheric sciences. How well are the two arenas gelling together? I mean, they seem to be sort of talking about very similar things, but I'd like to know what the points of contention are that are really sort of troubling the groups or the camps, or how well they're able to work together, and to what extent understanding biological systems and understanding atmospheric systems can ultimately kind of work together, or if they, or also maybe if you could clarify if they kind of operate on fundamentally different principles that makes them almost disciplinarily divided. Thanks.
Okay, I'll start. Some of my best friends are ecologists, actually. That is literally true. Back around the early 1980s, when the effects of vegetation on the land surface were first being talked about in the context of climate modeling, there was a tremendous amount of skepticism, which I'm sure Dave Schimmel remembers too, about the importance of things like stomates and intercepting rain on leaves as it falls and that kind of thing. And people said, they've gone off the rails, they shouldn't be talking about this. But now it's appreciated that in fact these things really are important, and that things like the carbon feedback in climate change are potentially very large and quite uncertain currently, and this is a major area for research. So I think we're a happy family.
Yeah, I think that that's largely true, although I remember when we were not a happy family. I moved as a relatively young scientist trained in biogeochemistry, which somehow lies uneasily at the interface of atmospheric science and ecology anyhow, to the National Center for Atmospheric Research. And I remember sitting in my office wondering how long it would be before I understood what geostrophy was or a gravity wave or all these lunch table conversations. It is possible to learn, and actually, hopefully the future Dave Schimmels will be able to...
How long was it?
It was a long time. I think that there are two areas where it's been technically and conceptually difficult for atmospheric science or geophysics and biology to come together. One is something that I alluded to in my talk, which is that one of the major controls over the surface energy balance of the entire planet is the stomate, which is a very, very tiny thing, and different species are different, even different leaves within the vertical coordinate of a plant canopy are different. And so there's a great challenge in extrapolating what we know about cellular and biochemical mechanisms to the average, if you will, or the integral of those cellular and biochemical mechanisms over the entire planet. And the second real conceptual challenge that as a community or as a big happy family, as Dave said, we're just beginning to grapple with, the rules that organisms follow as they process carbon, grow, change their density, and hence the reflectivity or the albedo of the planet. Those rules are set by several billion years of evolution. They're not derived from some sort of underlying physical first principle, although they're consistent with those physical first principles. So much of what we have to model about or understand and then model about the biology of the planet depends on evolution. And evolution is a historical science. It's not a first principles theory-based science in exactly the same way that geophysics is. And bringing that perspective where at some point you have to say, well, these plants do what they do because. And after the because, you're basically describing the history of life on Earth. That's very difficult to match with the scientific paradigm that we use in climate models, and we're really just beginning to grapple with that problem. But as we look at the migration of species and the rules that they will follow in doing that, as we look at the influence of invasive species, the rules in which those biological processes play out are set by evolution, and they include a contingent dimension. They are the way they are because of the way it was. And that's a real intellectual frontier. I think it's a very exciting area. It isn't mostly a contentious area. It's an area that's drawn the attention of very, very bright people.
I think the only thing I would add, it's almost a historical question in the sense that 30 years ago, climate modeling was dominated by people who had training in physics, and it was primarily physical processes which would go into the large models used to predict weather and climate. And you know, climate evolves, science evolves and advances, and these days we're grappling with the difficulties of putting biological processes into models and integrating them with the physics. And the scientific challenge is that biology is 10 times more complicated than physics, which is why I've never gone into it. But it may not have 10 times as much importance on the climate system. It may have equal importance. So the scientific challenge is to try and distill the biology and make it, and be able to integrate that into a climate model in some coherent way. I mean, climate models and climate science is evolving in many ways. Not just biology is going into it, but things like the great land ice sheets are now being incorporated into climate models, and that was something else that was unheard of 20 years ago. So, climate advances. Any other comments or?
Well, in that kind of historical perspective, it was hard to get the physics right, but got that. It would be even harder to get the biology right, but then it's even going to be harder than that to get the reaction of human societies right to that, and that'll probably have some unknown effect. I have no view of this matter, but that's going to be a hard thing, which will be much more, even more difficult to incorporate, and may have a substantial effect. I can't say that; I'm just saying it could have.
Well, I understated, and Dave understated the uncertainty in projections of future climate. I said that the carbon cycle for any given emissions pathway roughly doubles the physical uncertainty. But those uncertainties are dwarfed by the uncertainty associated with what fossil fuel emission future we might choose within the limits, as we understand them, of the amount of carbon available in fossil forms on the planet. So I think that if you take the carbon cycle as one central organizing theme, you can see that physics are uncertain, the biology is uncertain, perhaps twice as uncertain. But that figure, if it also showed the different emission possibilities from eventually going to a zero carbon future through simply burning everything as fast as we can, that's a much bigger uncertainty than any of the uncertainties we model today.
Yeah, I agree. We can't predict what the economy is going to do. We can't predict war and peace. We can't predict technological change, and we can't predict who's going to win the election. So what makes us think we can predict the fossil fuel emission scenario over the 21st century? That's by far the largest source of uncertainty for what's going to happen.
Any other comments?
I can't stand to see 15 minutes go to waste. And I want to address something this gentleman raised. You said, you implied that the problem was people who deliberately misinformed the public. But I feel it's a greater problem than that it's the public themselves who are increasingly distrustful of science in general, and it includes distrust of vaccines, distrust of our predictions, denial of evolution. I think it's a terrible problem, and to the extent that I can imagine a solution, it's greater transparency, greater scientific integrity, and perhaps greater policing of our own field. But people have to see that scientists have integrity, and once they lose that belief, we're all going to sink together. The doctors, every scientist is going to sink together. So that's a fear about mine. I don't know if you have a solution.
So we just had a comment to that. I fully agree with you, but the point you made about vaccines is interesting because I think a lot of the concern there is not around the science or the medicine, it's about the motivation of promoting medicines by big pharmaceuticals. So that raises the question of the links between science and industry. And a lot of the concern is about the big corporations and what's their motivation, whether it's GM crops or vaccines or whatever. And how do scientists retain their integrity and independence, but they need the money to be able to do the research.
Go ahead, use the microphone, it's right next to you.
No, use the microphone.
Oh, you want me to use the microphone? Okay. No, it's awful tall. No, I was just going to say that I think that the public at large seems to be intimidated by science in general, whether it be politicians, whether it be the general public. And I don't think this is on. Is it? Okay.
Yes, it is.
And I think there's a responsibility on the part of the scientists themselves, which you're doing here, is to try and translate this more into consumer speak. I think that politicians, if they're intimidated by science, they don't want to admit they don't know. So they're not going to make policy decisions, and the consumer and the public is going to listen to whatever sound bites that they hear. So there is a great responsibility on the part of the scientific community for this cross-pollination that you're doing between disciplines, and to come up with some sort of a common language so that it makes it more accessible to the public, to the policy makers, etc.
Go ahead.
We agree.
I think we agree.
Could you just, you had one scenario described, Professor Randall, on the, when I think it was, it took all the CO2 out of the environment and the water vapor followed suit. And could you just describe that? I didn't quite understand what the nature of that experiment was, or that.
Okay, the point of the exercise was to show really a couple of things. One is that the presence of non-condensing greenhouse gas like CO2, it condenses on Mars, but not on Earth. A non-condensing greenhouse gas like CO2 makes it possible for the water vapor content of the air to be larger, and that's another greenhouse gas, so it helps to warm the planet. And that if we take the CO2 out, that this leads to a cooling, which leads to less water vapor, which leads to more cooling, okay? And we fall off a cliff into a at least half ice-covered planet. So part of the point was to show that even though there's 4 times as much water vapor in the air today as there is CO2, the CO2 is still crucial. And part of the point was to, and I didn't really explain this clearly, but part of the point was to dramatically show the difference between a condensable greenhouse gas and a non-condensable greenhouse gas. So the reason water vapor is a feedback and not a forcing is partly because it's condensable.
Thank you.
There's a question at the back.
Do any of you know of any atmospheric programs being done anywhere across the world that are attempting to reduce the exposure of radiant energy entering the Earth? And if not, it's actually a 3-part question. Has it been done in the past that you know of? And again, if not, is there anything you can think of? Would it be possibly feasible? Is it even worth thinking about? Did you understand those 3-part questions?
Possibly. I think you're asking about geoengineering. So there are various ways of doing this. One way is to put sulfur particles into the stratosphere. Another way is to artificially increase the amount of cloud near the surface by injecting little particles. And another way might be to put some material between the Earth and the Sun out in space.
Anybody trying to do that now?
I hope not. One of the things you can say about it is that it's difficult to predict all of the effects of such an experiment, if I can call it that. So people are nervous that even though you might cool the planet, you might produce other changes that you don't like. You might shift the distribution of rainfall away from places where you need rainfall. But of course, a single nation, a single big nation, could potentially undertake a program like that on its own. And so there'd be issues about, you know, how do you respond to something like that? How do you prevent something like that? So there are all kinds of policy issues as well as technical issues here, but there's a lot of discussion of this, and it will be discussed in the forthcoming IPCC report, the one that comes out in 2013. But, you know, you can find lots of work on this out in the literature.
There was an experiment proposed and funded in the UK, which was ultimately blocked from being conducted. So most of the modeling and analyses that are being done in this arena right now are being evaluated against natural injections of aerosols into the atmosphere, for example, by volcanoes.
Maybe I could respond to that. My name is Alan Roebuck. I'm from Rutgers. I have several NSF grants to study geoengineering, and it's all indoor work. We do climate modeling. We study volcanic eruptions. I got called by a couple of people working for the CIA last year. They said, our job is to find out if some other country was controlling the climate. Could we tell? Would we know? And the answer was, yes, we would, because we can measure very small volcanic eruptions with current satellites and ground-based systems. We look at clouds all the time, and if you modified either of them enough to really cause the climate to change, it will be obvious we would be able to see it, and it's not happening. There's this chemtrails conspiracy theory that people see contrails in the atmosphere, which are water clouds coming out of jet planes, and they say that proves the government is trying to control the climate and it's putting bismuth in and it's killing everybody, but that's a wild conspiracy theory for which there's no evidence.
I have a question for Professor Randall. You present this sort of business card argument for global warming, and sort of my skepticism is to say that the feedbacks may be negative. So some of the cloud processes you discussed may ameliorate the warming. Do you have a sort of succinct argument that argues the other direction? Or?
Yeah, the cloud feedbacks are significantly uncertain, as is reported all the time in the press, and it's true. But the evidence today is that the cloud feedbacks are actually somewhat positive overall. Now, it's complicated. There are many different kinds of cloud feedbacks. It's not just one number. Changes in low clouds, changes in high clouds, and so on. But today's models produce moderate positive cloud feedbacks, and the reasons for that have been analyzed in pretty great detail. And especially the part of the feedback that comes from high clouds, cirrus clouds, is understood pretty well today in terms of a theory proposed by Dennis Hartman and colleagues at the University of Washington, basically involving constancy of the temperature near cloud top. So we're pretty confident that at least that part of the cloud feedback is positive, but there are other cloud feedbacks in the system associated with, let's say, low clouds that could possibly be negative, although it doesn't look like it. At any rate, a negative cloud feedback would have to be pretty strong to counteract the positive water vapor feedback and the positive snow and ice feedback, and perhaps the positive carbon feedback.
Looks like we're... Any other questions or comments? Yeah.
The Great Barrier Reef in Australia has been in the news recently about its size reduction by 50%. You care to comment on that?
Every ecologist has a favorite ecosystem. Mine are high elevation forests. And every ecologist claims that their ecosystem is the miner's canary of the climate system. It's the most sensitive. But the coral reefs actually probably have the best claim to that status because they're both sensitive to temperature change. They're sensitive to the carbon cycle directly through the pH of seawater, which responds to increasing absorption of CO2. And they're very sensitive to changes in human land use through sediment production, which blocks or essentially obscures the sun for the photosynthetic bottom of the food chain organisms on the reef. The Great Barrier Reef is affected by all three of those phenomena. There have been bleaching events that kill coral through high temperatures. There's a lot of sediment being transported as a result of agriculture that is killing some of the nearshore parts of the Great Barrier Reef. And there's increasing evidence that changing pH is beginning to have a direct impact on reefs. There are many other reasons in the paleo record why reefs are important indicators of global environmental conditions, and there's really the main challenge with reefs is figuring out which of these processes, including overfishing and actually direct use by humans, which of these mechanisms are having the largest effect. Or even just parsing them out quantitatively is very difficult, and they may be interactive. But it's not just the Australian Great Barrier Reef, it's reefs globally.
Yeah, okay.
So I'm glad you cued me into something that you're passionate about. Can you tell me how are the high altitude and mid altitude forests doing? Could you give me a status update in your perspective?
That's a very hard question to answer because mid-latitude forests and montane forests in that region are under a huge variety of stresses, but they're also, in many cases, regrowing from forest harvest that occurred between, say, 1850 and 1950. So on balance, the best we understand is that mid-latitude forests, including montane forests, are generally growing. They're taking up carbon, and in many areas, they're increasing in area. At the same time, they're being adversely affected by increasing drought in some regions, by atmospheric pollution deposition in many regions, and by direct human impacts through tourism, water use, and so on. So coming up with a cumulative scorecard, I think, is actually, although there have been a number of attempts using satellite data, it is really beyond our capability right now. We don't know very well how to integrate and sum all of these combined effects, multiple stresses, some people call them, that are occurring in that most intensely settled part of the planet.